In this video, I am going to walk you through all the fundamental principles of complex numbers to prepare you for more advanced challenges around the topic. Now, if you were to put this in your calculator, say x equals square root of some negative number, doesn't have to be -4, your calculator would have no answer, and you can prove me wrong by trying to do that. Now, what happens is in maths, this is where complex numbers really start, because this here, since the calculator has no answers, it seems to be some sort of imaginary or complex numbers, as the topic is called. And what happens is we assign a specific letter for this in maths. So whenever we use j, that's going to be equal to -1. So j will be seen the same as -1. So we use the letter j to represent the square root of -1. Now, there are a few things that this allows us to do. So for example, if we were to do j squared, then that would just give us -1 as the answer. And the main reason for that, I'll just drag your memory a second here. Let's say we do the square root of 25. We do know that the square root of 25 is simply 5. And we can replace 25 with 5 squared. So if we were to square root a squared number, then the answer itself would just simply be the number itself. So that's coming from the same principle here, where if we were to then square, let's say what we had was 5 like that, and we were to square that, then again that would still give us just 5. So if we do j squared, we end up with -1, because j squared is the same as us doing this, just squaring the square root of -1. So that's the first bit there. So j will represent root -1. Now we have two main formats that we're going to look at that defines a complex number system. One of them is called our Cartesian. So that's our Cartesian form, and that will simply be z, which represents our complex number, equals a plus, we'll use j, b. Now in this, remember that j represents our root of -1, and we'll have a, which will represent our real number. So this is typically seen as the real part in the complex number, and b is our imaginary part. Now this allows us to do a few things. We can represent this now on different formats. So one of them is something known as the Argand diagram, which is one way to represent complex numbers as a vector, and I'm going to show you how that is done now. So think of this as our coordinate grid, and j will be on the vertical axis, so this would be our j axis, and on our horizontal axis, then this will be our real axis. So that's our real numbers. Now let's say we had something like z equals 4 plus j3. Then what we do, we represent the 4 on our real axis, because the 4 is our real number. So on this axis we would have 4, and on the vertical axis we'll have 3, like that. So as a vector, or on our Argand diagram, I'll write that out for you. So it's ARGAND diagram. We represent complex number as a vector here, and this will look something like that. So this would represent our z equals 4 plus j3. Now this is just the same as if we were representing coordinates, because let's say for some reason, instead of having j3, what I have is negative or minus j3. So instead I'll have z equals 4, take j3. Then the 4 is still positive, so that will still be on the right of our horizontal axis, but now the 3 is negative. So what we would have here is our -3 down here, and the direction now of this vector will change, so it will go down and to the right like that. And this now is what would represent our 4 take J3. So it's just the same as we would use our coordinate system. So to the left of our horizontal axis, this would be our negatives. To the right, these are our positives. And going up, these are our positives. Going down, our negatives. So just as you would represent coordinates, it's the same way you need to think of the Argand diagram. So that was the Cartesian form, and we have another form called the polar form. And with this, you will have something similar where Z represents, again, our complex number, and you will have R, which is our magnitude, and we have the angle here, which is our argument, or you can just simply call that the angle. And we can represent just the same as we did previously. We can represent this again on our Argand diagram. So if I'm to just draw up a sketch like that, then let's say we had something like Z equals 6 and 30 degrees there. So the 6 would represent our magnitude or our resultant, and the 30 degrees would represent our angle. Now our 6 and 30 would be represented just like that. So our 30 degrees would be found right there, and our 6 would be R equals 6 for our resultant. And you would typically get some units, so I'll just put 6 units there. So depending on the principle, you'll get whatever the unit is. And of course, our axis will be labeled just the same as before. So this would still be vertical axis as our J axis, and our horizontal axis as our real axis. Now, one thing about the polar form is how you measure the angle. So let's say, for example, instead of having Z equals 6 and our angle being a positive 30, this could have been, let's say, Z equals 6, but now we're going to use negative 30 instead. And what happens is, for positive angles, we measure counterclockwise from our horizontal axis to the right. And if it was negative, then we measure in a clockwise direction from our horizontal axis to the left. So just by changing the angle from negative to a positive here, then from positive to a negative, what we end up getting is this now. And this would still be R equals 6, but this angle now would be right there. So we would measure this angle, the negative angle, in that direction, whereas the positive angle goes there, like that. So what that means is, for any angle that we can think of, there are at least 2 ways that we can measure it, and I'll show you that now. So let's say I've got an angle in this quadrant, and of course still our real axis and our imaginary axis. So let's say our angle was 60 degrees here. Then we would not use the 60 degrees that's between our vector there and the horizontal, because we would be measuring counterclockwise from here, from this point. So this angle would be measuring like that. So we would measure the angle here. So let's say we have some R value as, let's use 7. Then what we'd have here is Z equals 7, and our angle would be 120. So that's how we would measure our angle. Now, saying that our angle is 120, that doesn't mean it's the only way we could measure that, because If that's going counterclockwise to the left, which is positive, then what we could do is the other direction here, which is like that. But that angle will have to be stated as a negative. So for the same question, we could simply write this down as z equals 7 angle. And if you take that 120 from 360, then that would be negative 240 degrees. So we have two ways to measure our angles there. Now, what I'm going to do next is just to show you how we would convert from one form to the next. So let's say we're going to convert from our Cartesian form and we're going to go to polar form. Now, moving from Cartesian form to polar form is quite straightforward. So let's say what we have here was z equals 4 plus j3. And of course, we could have represented this on our argand diagram and measure up the angles, get what the resultant is. But for now, I'm just going to show you how to do the calculation. So what we would need to do, we need to work out our resultant, and that would just be the square root of our 4 squared plus our 3 squared that we have here in our Cartesian form. And when we do our 4 squared plus 3 squared, we're going to get 5, and I'm going to just use that as newtons to represent force. So that gives us our R value. And then let's find what the angle is. And that's always just going to be tan inverse. And we use vertical, which is the imaginary part. So that would be 3 over 4. So vertical over horizontal. And that gives us our angle, which is 36.87 degrees. Our final answer now then would be in polar form, z equals 5. I'll still use newtons, and like that, our angle. So that's how we would move from Cartesian form to polar form. Now, let's look at it the other way around. Let's go from polar form into Cartesian form. Now, for this, I'm just going to use the same figures that we just calculated. So let's say we have 5, and that's our resultant, our angle, 36.87 degrees. Now, for this, what we do, we need to work out our real part and our imaginary part. So since the format that we have here for Cartesian form is this, it's z equals a plus jb. So if we work out what our a part is, which is our real part, and our imaginary part, which is our b part, then we just put those answers in. And for our real part, we would have a equals r cos angle. And we know what the r value is. In this case, it's just 5. So we do 5 cos, and our angle, 36.87 degrees. So that would work out for us our a part. And we would expect to get the same as we had before, which is a 4. And our b part would be quite similar, but instead of cos, we have sin. So r sin angle, and again that would just be 5 sin 36.87 degrees, and what we would expect to get here again is around 3, and all we'd need to do now is just to put this together. So what that would look like is z equals, so a, which is 4 plus j3. And that would be us being in Cartesian format. Now, as a whole, complex numbers goes a very long way. So these are just some of the fundamentals that we need to know. And in the next couple of videos in this series, we're going to dive a bit deeper. So if you enjoy this type of content, please subscribe to the channel and give the video a thumbs up. And you can check out our catalog for a lot more maths and mechanical engineering content. So until next time, I will see you in the next video.